In this video, we are going to learn how to use double angle formulas to solve trigonometric equations. We're going to solve each of these equations on the interval of 0 to 2 pi, not including 2 pi. So now first I'm going to see here I have sine of theta times cosine of theta is equal to negative 1/2. Now if this was equal to 0, this would be an easy equation to solve because we can set each factor equal to 0, but it's not. But what this does look dangerously close to is the double angle formula for sine, which is sine of 2 theta is equal to 2 sine theta times cosine of theta. Because of how close these are, I can rewrite this to look just like this on the right, 2 sine theta cosine theta, by multiplying each side of the equation by 2, giving me 2 sine of theta cosine of theta is equal to negative 1 when I multiply the right side by 2 as well. Now I can rewrite this as sine of 2 theta is equal to negative 1. And now I just have to figure out what angle makes sine equal to negative 1. That would be 3 pi over 2. Now I want to get all of the angles on this interval, so I'm going to use the general formula because I have a period change going on in my trig function. Because if I divide each side by 2, I get my general formula to be 3 pi over 4 plus pi k. So now I just need to plug in values of k until I find all of the possible solutions on my interval. If I were to use negative k, I'd be subtracting a pi, which for negative k, negative 1, that would be negative pi over 4, which wouldn't be on my interval. Now, if I use 0 for k, that would just be 3 pi over 4, which is on my interval, so that's one of my solutions. If I use k is equal to 1, I get 3 pi over 4 plus pi, which is 7 pi over 4, which is also on my interval, so that's another solution. And if I add any more pi to this, it will go up to 11 pi over 4, which is now outside of my interval. So that would not be a solution. So my two solutions are 3 pi over 4 and 7 pi over 4. Now whenever you have a period change like this, you need to check your general formula for all the possible solutions, just in case you have more than one. Because right here we only got 3 pi over 2 and then 3 pi over 4, but because we used the general formula, we also found 7 pi over 4. Now for this next example, I have cosine of 2 theta plus 6 sine squared of theta is equal to 4. Now they aren't the same trig function, but I can rewrite cosine of 2 theta using a double angle formula as 1 minus 2 sine squared theta, which will make all of these into sine thetas and all the same angle as well, because now the 2 theta becomes a single theta. So now I have 1 minus 2 sine squared theta plus 6 sine squared theta is equal to 4. If I subtract 1 and combine my sine squareds, I get 4 sine squared theta is equal to 3. Divide by 4, and I get 3/4, and then I can take the square root of each side, giving me sine of theta is equal to plus or minus the square root of 3 over the square root of 4, which is 2. So I need to know every angle that makes sine either positive or negative square root of 3 over 2. And this time I won't check my general formula since I'm not dealing with any period change here. So all the angles I find on my unit circle will be all the solutions. So first I'll start with my first quadrant. A positive square root of 3 over 2 happens at pi over 3. Another positive square root of 3 over 2 happens at 2 pi over 3 in my second quadrant. In my third quadrant, I get a negative square root of 3 over 2 at 4 pi over 3. And I get another negative square root of 3 over 2 in my fourth quadrant at the angle 5 pi over 3. So these would be my 4 solutions to that equation. Now these next two examples on the right are a bit more involved, so stick with me as I get through them. So this first one, I have sine of 2 theta plus sine of 4 theta. Now these two angles aren't matching, But I can use my double angle formula for sine specifically on this 4 theta. Because the way that would work for sine of 4 theta, I would get 2 and then half the angle down. So now I wouldn't go down to theta, I would go down to sine of 2 theta and cosine of 2 theta. So I can rewrite this as sine of 2 theta plus 2 sine of 2 theta cosine of 2 theta. Now what's nice is that this equation is equal to 0. So if I can start factoring, I should, and I can see that each term has a sine of 2 theta in it. So I can factor out sine of 2 theta. And on the inside, I'll be left with 1 to replace that sine of 2 theta plus 2 cosine of 2 theta. And I guess that each factor equal to 0. So sine of 2 theta is equal to 0, and 1 plus 2 cosine of 2 theta is equal to 0. Solving that equation on the left, I get cosine of 2 theta is equal to negative 1/2 from subtracting 1 then dividing by 2. And now I see I get over here what makes sine equal to 0. Well, it happens at 2 angles on my unit circle, and I'm going to write the general formulas down. It happens at angle 0 plus 2 pi k, and it happens at pi plus 2 pi k. Over here, when does cosine equal negative 1/2? That happens in the second quadrant at 2 pi over 3. And in the fourth quadrant at 4 pi over 3. Again, plus 2 pi k for the normal period of cosine. And now we'll divide by 2 in all these equations. And my general equations now become 0 plus pi k, pi over 2 plus pi k, pi over 3 plus pi k, when I divide 2 pi over 3 by 2, and 2 pi over 3 plus pi k. Now I'll use these general formulas to find as many solutions as possible. I'll start with my very first one. I can use 0 if I use 0 for k. If I use negative 1 for k, I would subtract and I would go outside of my interval. But if I use positive 1 for k, it'll be pi, so 0 plus pi is pi. If I use 2 pi would almost be my interval, but I don't include 2 pi, so now I'm tapped out from that equation. So on to the next one. I can't use a negative k because that would go backwards by at least 1 pi, which puts it outside of the interval at negative pi over 2. So I'm going to stick with 0 first, so pi over 2. Then 1k gives me pi over 2 plus pi, which is 3 pi over 2. And another pi would be 5 pi over 2, which is outside of that interval. And you start to see a pattern here that I'm getting 2 from each of these, just like I got 2 from this general equation over here. Whenever I had 2 theta, I found 2 solutions. So from each of these, I should get 2. If I continue onward, I can get pi over 3 as a solution. Adding pi, I can get 4 pi over 3. The next one, I can get 2 pi over 3. And add another pi, I can get 5 pi over 3. Any other values of k would not yield any solutions for the equation. Now for the next equation, I'm not going to use the double angle formula for tangent because it would just yield more tangent of thetas and not help me get rid of the sine of theta. So instead, I'm going to use the double angle formula I'm going to use the quotient identity for tangent first, and then use the double angle formulas for sine and cosine to find a solution. So first, I'll start with rewriting this as sine of 2 theta over cosine of 2 theta plus 2 sine of theta equals 0. Now, I can factor my numerator to be 2 sine of theta times cosine of theta, and that will yield a common factor of sine for me to factor out. And for right now, I'm just going to keep this as cosine of 2 theta until I see what happens after I factor. So if I factor out a 2 sine of theta from both terms, I'll get 2 sine of theta times cosine of theta over cosine of 2 theta plus 1 equals 0. My left factor can be set equal to 0. 2 sine of theta, which means sine of theta is equal to 0. And I'll come back to that in a little bit. And I have this factor I can set equal to 0, so I'll move over here to give me more space. So I have cosine of theta over cosine of 2 theta plus 1 equals 0. Well, first I can subtract 1, give me cosine of theta over cosine of 2 theta is equal to -1. And then I can get this cosine of 2 theta out of the denominator by multiplying it to each side, giving me cosine of theta equals negative cosine of 2 theta. And then I can add it back to the left so I can start to factor, hopefully. So now I have cosine of theta plus cosine of 2 theta is equal to 0. Now, these aren't the same angle on the inside, so I can't combine them, nor can I factor yet. But I can use a double angle formula for cosine to reduce the angle down to a single theta. And I'll use the cosine squared formula in order to do this. So I'll get cosine of theta plus the cosine squared formula for cosine of 2 theta is 2 cosine squared of theta minus 1. And now I have a quadratic that I can factor. So 2 cosine squared theta plus cosine of theta minus 1. And if I factor this quadratic, I can get 2 cosine of theta minus 1 times cosine of theta plus 1 equals 0. I know it's getting squinched in, but those are my 2 factors. So I can set 2 cosine of theta minus 1 equal to 0 and cosine of theta plus 1 equal to 0, giving me cosine of theta is equal to 1/2 and cosine of theta is equal to -1. So now I have these 3 equations, which I'll star with red stars so you can see where they all are, that can give me all the solutions I need for this equation. So first, sine of theta equals 0. That can happen at 0 and pi, as well as 2 pi, but that's outside of my interval. Cosine of theta can equal 1/2 at pi over 3 in the first quadrant and 5 pi over 3 in the fourth quadrant. And lastly, I have cosine of theta can equal -1. Well, that can only happen at pi, but it's already listed. So my 4 solutions are 0, pi, pi over 3, and 5 pi over 3. So sometimes these equations could take a little bit of effort, but once you start solving a few of these, you'll be able to solve them quicker and quicker as you start to see the patterns earlier. And that is how you use double angle formulas to solve trigonometric equations.